New to this course or listening to me first time, I think most of you have attended my last class, right? Is there anybody new to this class? Most of you have attended my earlier classes. Respond to me.
There aren't any newcomers.
Huh?
There aren't any newcomers.
There are no newcomers, right?
Yes, sir.
Okay. So last class, we have discussed fundamentals of the biasing. I have just taken this circuit. This is not an amplifier circuit. It is just a part of the circuit. Okay. 1 minute. I will turn off my notification. Okay. So this is not an amplifier circuit, but it is a part of the amplifier circuit, which you can call this as a bias circuit. Okay. And later we explained the transfer characteristics of this device. Okay, the circuit what we have shown. 1 minute. Yeah. So this is the transfer characteristics of the circuit we have shown. If you observe this transfer characteristics, that is a graph of V naught versus Vi for this circuit. Okay, this is simple BJT circuit, which you can see here. There is a BJT here and there is a collector resistance here, and the VCC, which is a collector power supply. This is simple circuit. For this, if you plot a graph of V naught versus Vi, the transfer characteristics looks like this. Okay, so this is the transfer characteristics. Okay, which you can see here. This is complete characteristics is non-linear in nature. Okay, and if you observe the whole characteristic, it is non-linear in nature, but some part of the curve which is going to be a linear in nature, especially this mode called as active mode, which is linear in nature. But other modes such as cutoff region, cutoff mode or saturation mode, these are non-linear in nature here. Now when we want to use BJT as an amplifier, we need to operate BJT in the active mode. So here BJT works like a amplifier. So BJT works as a amplifier, whereas here in the saturation mode BJT work like a on switch. When we want to use BJT for switching function, especially for on and off as a switch, it can be operated in saturation mode. So preferably in saturation mode BJT works like a on switch, and in cutoff mode BJT works like a off switch. Okay. Now just we want to change the input voltage, that is all here. When we want to use BJT as a half switch, just make input voltage lying between 0 to 0.5. So BJT will be in as a, it works like a half switch, and when you make input voltage greater than say approximately more than 1 volt up to 1.5 or 2 volts, the BJT behaves like a on switch here. So we are not interested in this course of usage of BJT as a off or on switch, but mainly we are interested in using BJT as a amplifier here. Okay, so for BJT to work like an amplifier, we must operate in the active mode. In active mode, you can observe that this transfer characteristics is to some extent it is going to be a linear. Now in this linear mode, if you apply the input signal, which is sinusoidal here as an input to the circuit that we have shown, and the output signal is going to be an amplified version here. As you can see here, the negative going signal will be a positive going signal here at the output here, and the signal strength also you can observe here. Here the input signal is, so this is going to be the input signal, and here we have output signal here. The signal strength you can observe here, the signal magnitude is going to be larger in strength, whereas here input signal is a weak signal. Usually the weak input signal is going to be in terms of 50 or 100 millivolts here. So this is the characteristics we have seen in the last class, and later we have discussed about notations which we need to be familiar with the amplifier circuits. The smaller case, okay, 3 types of notations we have discussed here. The first notation kind of notation is both uppercase letter and uppercase subscript, that is called DC notation, and later we have AC notations which you can see here, both lowercase letter and lowercase subscript, this is for AC notation, and the total values. Okay, so whenever we indicate lowercase letter and uppercase subscript, so this gives me the total value. Okay, it may be the voltage or total value of it may be the current here. Okay. Following which we have discussed even biasing also. So we defined what is biasing. Later we have taken 2 different kind of the biasing schemes as an example. These 2 biasing schemes are not good biasing schemes. Reason I will just brief you in shortly. First one is going to be biasing by fixing base emitter voltage. The circuit diagram for this is as shown here. So this is the circuit diagram for biasing, okay, the amplifier circuit with fixed VBE. The voltage here VBE is going to be fixed here. Okay, so this voltage here is derived from the supply voltage here. So you can see here this branch here what you are seeing, which contains resistors RB1 and RB2. The supply voltage, collector supply voltage is divided across these 2 resistors, and a constant voltage is available at this particular point with reference to ground, and here this voltage is applied as an input for the BJT here, and this voltage is labeled as VBE, base emitter voltage here, and now you can see that the output voltage is VCE. These are all DC voltages here. We need to set up constant DC voltage across the transistor circuit, so that any signal applied here, a sine or cosine, okay, so that get amplified here when the biasing conditions are established here. So with the help of biasing schemes, we are establishing constant voltage here and constant currents here. At any instant of time, the output current should not vary with the transistor parameters here. That kind of the concerns we have to ensure here. Okay. So this is a scheme wherein which base emitter voltage is kept constant here. But unfortunately, as we have shown in the last class, the collector current here that is flowing in the this collector resistor and the base emitter voltage VBE, they are related in an exponential way. So last class I showed you that equation. So this IC, which is equal to reverse saturation current times e to the power of okay, VBE, okay, by VT. So this is the equation, the collector current and its relationship with the base emitter voltage. As you can see from this equation here, since base emitter voltage is an exponential term, and any small change in base emitter voltage leads to a big change in the collector current here. This is a serious effect here, because the collector current should not change as the input voltage is fixed in this case here, but a small change here, maybe say if I prefer another circuit with VB change, say 0.7 to 0.5 to 0.7, if it varies, assume that this is a one circuit I am employing a VB as 0.5 volts. In another circuit, let us assume that VB changed from 0.5 to say 0.6 volts or 0.7 volts. As you can see here, there are 3 different values of VB I have shown here, and for 3 different values you can see that this collector current is going to vary in a large manner, because of this VB is present in the exponential of this equation here. Okay, this is the serious problem here. Okay, that is why this kind of circuits are not used in the biasing method here, biasing in an amplifier. Next type of biasing is biasing by fixing base current here. Let us see here how we maintain constant collector current in spite of variations of BJT parameters. Let us see that here. The circuit diagram for fixing base current is as shown here. This is again another biasing circuit here. Unlike earlier case, we maintain constant base emitter voltage, but here we are maintaining base current, not the base emitter voltage. Even here the base emitter voltage, we assume it is a constant, but though the variations of base emitter voltage exist here, but here we try to maintain the base current as a constant here. Now, let us see here this circuit how it works for the changes in the the transistor parameters here. Now, let us apply some mathematical aspects of to this circuit and analyze this circuit in more detail. Okay, now, let us apply Kirchhoff voltage law to the base emitter loop. So, base emitter loop which you can see in this circuit here, this is going to be the base emitter loop. When you apply KVL from this, okay, so you get this from here, which is minus VCC plus drop across, this is which is IB times RB, and we have here voltage, base emitter voltage plus base emitter voltage VBE equals to 0 here. So, the same equation is shown here, which you can see here, okay, minus VCC plus IBRB plus VBE. You can derive for base current here from this equation. Just rearrange this and find out what is base current equation. Next is we can substitute for base emitter voltage. Let us assume that base emitter voltage in this circuit is fixed at say 0.7 volt. So, now you can substitute in the base current equation 0.7 volt. So, the base current equation is this. Now, we know that from fundamentals of BJT, collector current IC is equal to beta times the base current. Beta is the gain of transistor in common emitter configuration. Now, we can substitute for IB from this equation here. Okay, once you do that, you will get collector current expression. That means, from input current I am trying to obtain the output current expression here. IB is going to be the input current for the circuit that is shown here. Look at this circuit, IB is the input current here. From this I am trying to find what is the expression for the collector current here. So, we got to know the collector current expression is beta times VCC minus 0.7 divided by RB. Now, let us try to obtain output voltage, that is voltage across collector and emitter. Between these 2 points, let us try to obtain what is the voltage here. So, this is nothing but VCE, which is shown here. Now, let us try to apply Kirchhoff current law in the collector emitter loop, the loop which is like this, okay, collector emitter loop starting from VCC here. So, you can see we will get minus VCC and drop across, this is IC times RC, and we have VCE plus VCE equals to 0. You can simplify that is shown here. This is the Kirchhoff voltage law, same equation which you can see here. So, this is the same equation which is shown here, and you can rearrange and find out expression for collector emitter voltage, and you can substitute for this IC that we have derived here for the collector current. That means, from the output current we are trying to obtain the equation for the output voltage, which is collector emitter voltage. So, the final expression for collector emitter voltage is given by this here equation. Okay, so, VCE is equal to VCC minus beta times RC by RB into VCC minus 0.7 volts. So, now we got to know the expression for the output collector emitter voltage, and we also know expression for collector current here. Okay. Now, with this kind of the analysis, let us try to take an example and see that whether this circuit is whether it is robust with reference to the changes in the transistor parameters here. Ultimately, our aim is the circuit what we have designed here with the assumption of base current constant. We will see that whether this circuit is able to maintain constant collector current irrespective of variations in the transistor parameters and as well as even temperature variations also. Okay. For a given circuit, RC, RB, VCC and BJT beta, these are the given values here, The above equation can be used and you can find out the bias point IB, IC and VC can be estimated. We already derived equations for all these three unknown things. And you can also use these equations to design even BJT circuit, and also you can identify the operating point, which is bias point here. Now let us take an example of using this biasing scheme here. This is the circuit given here. We need to find values of RC, RB. This is already shown here. You can see in the circuit for the figure which is shown here, and here the given values are beta as is shown given as 100. Collector supply voltage is given as 15 volts, and the bias point is also given to you, which is the operating point of this transistor. This VCE and IC are called as operating point. Okay, so here in this case it is given which is 25 milliampere, and VC is going to be the 7.5 volts. Okay, so this is the these are the voltages which are given. All right. Okay, so with that let us see that whether we can able to find these values of RC and RB or not. Let us see now whether BJT is operating in the active region or not, that we can find out. The condition for that is VCE must be greater than VBE. So, you can see in this case VCE is given as 7.5 volts. So, this is VCE, and VB is already known, which is 0.7 volts, which is very small value. In this case even though it is not given, so VB is typically it is going to be around 0.6 to 0.7 volts. It varies for a given transistor here. Let me choose different thickness. Okay, so these are the different values of VBE. When we compare VCE and VBE, VCE is found to be greater than VBE. So, therefore, we can say that transistor is operating in the active region here. Okay. All right. Now, we can find out base current from this. IB is equal to IC by beta. So, we can substitute here IC and as well as beta. So, 25 milliampere by 100, that gives me IB base current as 0.25 milliampere. Okay, now let us find out the values of value of RB. Now we can apply once again Kirchhoff voltage law to the base emitter loop. Examination, you need not apply again and again this KVL to the base emitter loop. Once you since in the while analyzing this circuit earlier, we have shown that the KVL equation here, which is already there, straight away you can use it, and sometimes when you forget, you can apply KVL and then you can arrive at final equation here. Since this equation is already shown by applying KVL, I do not want to go back and apply KVL once again. So, from this we can derive the value of RB. RB is found to be VCC minus 0.7 divided by IB. Remember that VB was not given, here we have taken as 0.7 volts. You can assume VB value anywhere between 0.5 all the way up to 0.7 volts, even though it is not given in the examination. Sometimes in the examination they may not give you this value. So, students can prefer of VB values in between this range. Now, we can substitute here the value of VCC, which is 15 volts, and the base current already derived here, which you can see 0.25 milliampere, which you can substitute here, and RB is found to be around 57.2 kilo ohm here. So, this is the value of RB here. Next, let us find out the collector resistor. Similar KVL equation can be applied to the collector emitter loop. So, you can see in the basic circuit, this is the collector emitter loop. So, starting from supply voltage here till this ground here, we can apply KVL. So, this is the loop, collector emitter loop. Okay. So, this is the base emitter loop. Okay. So, this is a B loop, this is a collector emitter loop. Okay. So, after applying KVL to the collector emitter loop, which is minus VCC plus IC times RC plus VCE, that is going to be the equation. So, which is already shown here. Now, we can derive the value of RC. RC is going to be VCC minus VCE divided by IC, which is 15 minus 7.5 divided by IC value is going to be 25 milliampere here. So, substituting all these values and simplifying, calculating the value of RC, the value of RC is found to be 300 ohms here. So, this is the value of RC here. So, our ultimate aim here is now in this problem, the values of the currents and voltages are given here, especially beta of a transistor is given, supply voltage is given, and collector operating point is given. With this we estimated the resistor values RB and RC. In examination reverse also may be asked, by giving RC and RB and supply voltage and this base current, they may ask you to find out operating point also. So, student should practice in both the ways here. Do not look at the problem from one point of view, you should also look at from other point of view also. Okay. So, here the voltages and currents are given, we estimated RC and RB. So, this is called as a design, we designed the bias circuit with fixed base current here. Now, let us take further extend this problem with the different values of value of beta. Let us say now here, earlier we have worked out this problem by choosing beta as 100. Now, let us choose different value of beta and see whether what changes happens in the value of resistors and currents and voltages by changing beta from 100 to 200. So, this is another problem, example 2 with beta as 200 here. Okay, now we can we have RB value as 57.2 kilo ohm, which we have taken earlier. We will retain the same value of RB, and RC also will retain same value. VCC is supply voltage is 15 volts. Now, let us see that beta on what factors it depends upon. Even if you look at previous equations like IB, IC and VCE, let us see here IB, now you can see it depends on beta. The moment we change beta, IB changes here. Also you can see VCE also depends on beta, because once IB changes, VB also VCE also changes here, because see IB changes, IC also changes, once IC changes here, VCE also changes here. So, therefore, there is one-to-one relationship here. Okay. Now, let us see how we can solve this problem by using different values of beta here. Now, we can apply KVL once again. If you know already the KVL equation, you can straight away write here, and now we can derive IB from this. IB is as usual, which is VCC minus VBE divided by RB. So, IB is found to be 0.25 milliampere. Okay, next we can see that IB is taken as 0.25 milliampere. Now, collector current will change now because of change in the beta value. So, IC is equal to beta times IB. So, beta is now taken as 200 instead of 100 here. So, IB is fixed here, which is 0.25 milliampere. So, IC value what we got is 50 milliampere. We can observe here with beta as 100 in the previous problem, what was the value of collector current here. So, in this case the collector current value is 25 milliampere. By changing beta from 100 to 200, look at this value of IC. IC value has been doubled. Let me show that. Now, you can see that IC value from 25 milliampere for beta 100, it has been doubled to 50 milliampere for the beta value as 200. Let us see now what is its impact on the collector emitter voltage. Once again we can use same collector emitter loop equation, minus VCC plus ICRC plus VCE. From this we can derive for VCE. VCE is equal to VCC minus IC times RC. Since IC has been changed here due to the change in the beta value, so new value of IC can be substituted here, and you can derive the value, find out the value for VCE. So, once you do that, you can see that VCE value is going to be 0 here. You can observe now what is happening in the circuit just by changing beta from 100 to 200. So, you can see that VCE value has been reduced. So, VCE it has become 0 now, and it is now less than the base emitter voltage. So, from this condition what is going to happen, just think about it. Okay. Earlier we assumed that in the previous problem we said that with beta is equal to 100, what we said is VCE was given, which is 7.5 volts, that was greater than VBE. So, we said that transistor was in active mode, but now look at here, in this case VCE has reduced to 0 and that is less than base emitter voltage. Now, BJT switches from active state to cutoff state here. Okay. Since IC is greater than 0, it should be in the saturation region. So, in this case it is not cutoff, since IC is larger than 0. So, the transistor moves to saturation here. So, that is a problem here. Okay. So, we expect BJT to be in the active mode for during the amplification, but here due to the increase in beta value, the transistor moved from active state to saturation state here. Okay. So, this is a problem in with reference to this circuit here. That means, for the drawback of this circuit is not good circuit, it is a bad biasing schemes, because due to the change in the value of beta of this transistor, say this I may use a transistor with say beta 1 and another transistor I may plug with beta 2, that means the change in beta value changes this operating state of a transistor here. It moves from active mode to the saturation mode, which once this BJT moves from active to saturation, it stops amplifying action. Okay. So, that is a big problem in this type of biasing circuits. Now, let us see the variations with temperature now. If you look at this last paragraph here, so far we have shown that change in beta value changes the collector emitter voltage and it pushes transistor into the saturation from cutoff mode here. So, fixed bias circuit as a beta of a commercial BJT can depart substantially from its average value due to temperature change also. In a given BJT, the collector current increases 9% per degree Celsius for a fixed bias, fixed VBE. This is the variations, percentage variations, 9% per degree Celsius change in the temperature. Okay, this is how the collector current increases because of the change in the beta value. Okay. Now, if you want to design a circuit at say room temperature 25 degrees Celsius, and at 35 degrees Celsius you can see that beta and IC will be roughly, it will get doubled here. Okay. And the BJT moves into the saturation here. Okay. That means even the temperature varies, the collector current also increases, and that changes the value of collector current in the output circuit here. This poses a problem in the amplifier circuit here. Now, let us see in front of us, now we have a big problem now. What is the problem that is defined in the last statement here? The problem is that our biasing circuit fixes the value of IB, okay, by choosing proper resistor values. As a result, IC and VCE are directly proportional to the beta. Since using proper resistors we can fix the value of IB, but the collector current, like collector current and collector emitter voltage, they are directly proportional to the beta of a transistor. We already used told with reference to many equations how this IC and VC is proportional to the beta. Now we want to make this IC and VCE independent of beta. As conditions for BJT to be in the active are VCE and VB must be equal for IC greater than 0, and changes in BJT beta would change this bias point here. Okay. So, this is a problem here. Now, we have to maintain or design bias circuit such that the transistor must operate in the active mode, and also due to the change in the beta value or due to the change in temperature, the value of the collector current and collector emitter voltage should not change. So, this is the problem now. With that, I think we can arrive at simple solution. The solution is to design the circuit such that it would force collector current to be which you can assume as certain value, and VC and VB, that is going to be the voltage between collector and emitter, and base emitter voltage, let us make it these two values equal. Then even if beta changes, IC and VC shall remain fixed. Okay. BJT changes to IB to match a new value of new beta value here. That means even though we assumed here as VC and VB equal, Let us start with the some random value of the constant the current IC, and we assume that Vc and Vb are going to be equal, and even if beta changes we have to ensure that IC and Vc remains fixed, and even if BJT changes the IB should adapt itself here to the new beta value here. That is how we should design a circuit here. The entire problem what we have discussed, the solution we arrived at only this. So, next biasing schemes what we are going to discuss, in that kind of the biasing scheme, this the techniques are adopted here. Okay. Any questions so far? Okay. If you do not have questions, let me move on to the next good biasing schemes. Previous bias circuits that we have discussed are called as bad bias circuits, or they are not good bias circuits. Now, we are going to discuss here a good bias circuit or better bias circuit called as the classical discrete circuit bias arrangement. As you can see here, what changes you would observe in this circuit compared to the previous circuit? Any changes you see in this circuit? Pardon me?
Resistors.
Yes, this is an extra component which is added, right? Okay. Previously you have seen in conventional biasing schemes, in one circuit we have seen only RB, in other circuit we have seen 2 resistors. The same the trend is continued even here also, but only extra element that is added here is a resistor at the emitter terminal here. What is the advantage of adding resistor at emitter terminal? Any guesses?
To control emitter current.
To control emitter current, you can see here the same point is shown here, which you can see second point if you can read. The key to this biasing scheme is the emitter resistor, which is Re. This is the key resistor here. Compared to other biasing schemes, this circuit is much better. Reason is this uses a single power supply VCC, which is common for both the branches. This typically 12 to 15 volts, which you can prefer. This is collector supply voltage. With reference to BJT, we denote it as VCC, and when we discuss MOSFET circuit, same power supply terminology can be changed to VDD, that is a different drain power supply. Even the value remains same, which is of same value as this. Okay. And using this resistor Re, this provides a negative feedback. You can see here, this provides negative feedback. What is negative feedback? What is negative feedback? We are trying to say here this emitter resistor Re provides negative feedback. Okay. Shortly we will get to know that why this using this emitter resistor here, how this circuit adapts itself, the base current especially, whenever there is a change in the transistor beta value or transistor parameters, due to this emitter resistor, this complete circuit adapt itself to the new value of the currents and voltages. Okay. So, this is very important resistor called as emitter resistor. Apart from this, in this kind of biasing scheme, you are seeing a voltage divider network, which you can see here R1 and R2. This forms voltage divider network. Okay. So, this is voltage divider network. What do you mean by voltage divider network? What do you mean by voltage divider network? So, this branch here R1 and R2 takes supply voltage VCC and depending on the value of R1 and R2, the drop occurs across this. Suppose if I choose this value as say 1k and 1k, what may be the voltage drop? Any guesses? Assume that this voltage is 12 volts, VCC is 12 volts. 12 volts is here and R1 is 1k, R2 is 1k. What is the drop across this? Obviously, it must be 6 volts, right? 6 volts here and 6 volts here. Yes? This is another branch, right? And the voltage will get divided equally from supply to the ground, right? And look at here again, this there is a drop here, there is a drop across collector and emitter, and there is a drop here. Okay, there are 3 different segments here, divisions here. Some voltage get dropped here and some voltage will get drop across the collector and emitter of a transistor, and some voltage get drop across this. Okay, but here on another branch where we have separate supply voltage, we have a common supply for both the branches here. So, depending on the R1 and R2, the voltage here can be decided here. Okay. So, if I change the values of R1 and R2, definitely drop the varies. Okay, that is why this is called as a voltage divider network. The voltage divider network means it takes a supply voltage and divides the voltage across this depending on the resistor values here. Many times we need to design these resistor values. So, we apply Thevenin's theorem for this to obtain the voltage at this particular point. Okay. So, this is overall biasing is called as classical biasing of BJT, and this uses single power supply here. So, go through this circuit. If you have any questions you can ask. This is not again complete bias circuit, because here we need to apply connect a capacitor here, and for that we need to apply an AC signal like this. Okay, that gets amplified because we have to apply AC input signal that needs amplification through the capacitor here, because any DC here should will get eliminated through the capacitor here. And again here also in output part of the circuit we need to use capacitor here. These are called coupling capacitors. Okay, so these coupling capacitors are used at both input and output, and there are even bypass capacitor also. If you connect all those the capacitors across this circuit, that becomes an amplifier circuit. Since we are discussing this under DC, so this capacitor will not be used here, that is why we do not show this capacitors. Okay. So, this is the classical biasing scheme. This circuit overcomes a drawback of previous 2 circuits. We will see that how this circuit will overcome drawback of previous 2 circuits here. The technique consists of supplying the base of the transistor with a fraction of supply voltage VCC through the voltage divider network formed by R1 and R2. We already said about that. R1 and R2 forms a voltage divider network, and the fraction of the supply voltage, this supply voltage is VCC, that gets divided across these 2 resistors. Now, we can replace this voltage divider network with Thevenin's equivalent. Let me remove this. Just simplifying here this circuit. Okay, so let us see that how this circuit can be simplified. Now, this part of the circuit here, this part what I am circling it here. Okay, for this part we will apply Thevenin's voltage, Thevenin's theorem. We need to find out here at the base of the transistor what is VTH, Thevenin's voltage, and RTH. Okay. So, let us find out these things here. Okay. So, you can see here what is VTH here. Let me call here instead of this VTH for this our convention, let us indicate this as VBB. So, voltage at this point is equal to, if I call that as VTH or VBB, What is the expression for this? You can apply voltage division rule here, and what is the expression for voltage at this point here? It is VCC times, let me write here, VBB equals voltage at this point equals supply voltage times VCC is supply voltage times this resistor value R2 divided by sum of the resistor R1 plus R2. This is again voltage division rule. I hope you are all familiar with voltage division rule. When you want to find out voltage across any resistor, in this case it is R2. Okay, so we want to find out what is VBB. So VBB is equal to supply voltage times the resistor across which you are finding the voltage, which is R2 here, divided by sum of the voltage. Okay, so this is voltage division rule. Okay, so which is also equal to Thevenin's voltage. Now let us find out equivalent resistance at this particular point. When you want to find equivalent resistance, you must ground this DC voltage. When you ground this DC voltage, from looking at this point of view, this equivalent resistance RTH is nothing but these two becomes a parallel elements. It appears like this. There is a single point here and there is a resistance here which is going to the ground, because this DC supply voltage we have grounded here, and this point we call as RTH now, and this is R1, and at this point we have another resistor which is also going to ground. So, this is R2. Now, what is RTH now? At point RTH, this R1 and R2 becomes parallel. So, we can write here this R1 is parallel to R2. So, we got to know Thevenin voltage RTH, which is equal to R1 parallel with R2. Now, we got an equivalent circuit for the circled portion. We applied Thevenin's theorem and we estimated voltage at this point, which is given by this expression, and we estimated resistance across this, which is given by this expression. Now, the circled portion now will be equivalent to this voltage like this. Let us call this, instead of R Thevenin, I will give another name as RB. Okay. So, here we have an RB and here we have VBB, and this is the equivalent of this circled, okay, the portion of a network, and here this goes to the BJT, which is as usual. This part we are not at all disturbed here, we kept as it is, and resultant circuit which you can see here. Okay. So, this is the resultant circuit. As you can see, that expression for VBB is here. So, this is the expression, VBB is equal to VCC into R2 divided by R1 plus R2, and RB is nothing but R1 parallel with R2, and outer part of the circuit we are not at all disturbed here, we kept as it is. Okay. Why we have done this, applied voltage Thevenin's theorem and simplified this network, because when we have a voltage divider network like this, it becomes tedious to analyze the circuit. So, therefore, we have simplified this input part of the circuit by applying Thevenin's theorem. So, the Thevenin's equivalent, once it is applied to the original circuit, the circuit looks like this. Now, both circuits are equal. So, the only change is this circled network we have replaced with the Thevenin's voltage here and the Thevenin's resistance here. Okay. Rest of the things are same, we have not changed anything else. So, we have final expression for VBB, which is Thevenin's voltage, and Thevenin resistance is as shown here. Okay. Now, we know from fundamentals, for any transistor, emitter current should be equal to base current and collector current, and you can substitute for collector current as beta times IB, and you can take out IB as a common factor. So, the net expression for emitter current is IB times 1 plus beta, and we can derive IB from this equation. So, IB is equal to IE emitter current divided by 1 plus beta. This expression is required in the next equation which I am going to derive. So, the emitter current IE can be determined by applying KVL for the base emitter loop. So, now we can apply KVL for the base emitter loop in this way. Okay. What do you get it here? Minus VBB plus IB times R1 parallel with R2 plus VBE is there. You should not forget VBE. Okay, just to show here VBE. This is VBE and IE times RE. Look at how many terms you get it here. Rewrite here for your reference, minus VBB, that is supply voltage here, IB times R1, IB times RB. For the time being, let me write here IB times RB, where RB in turn is R1 parallel with R2, plus we have base emitter voltage plus IE times RE equals to 0. So, this is the equation which you can see here, same equation we have written. Totally there are 4 terms, as you can see even here also, totally we have 4 terms here. Okay. Okay, now we can simplify from this equation. You can substitute for IB, just now we showed IB is IE divided by 1 plus beta. Substitute here, this is IB substitution, and remaining terms you can leave it as it is. Now, try to find out what is IE. We have one term with IE here, another term IE here. Take out IE as a common factor and you can simplify this equation. IE is now equivalent to VBB minus VBE divided by RE plus RE divided by 1 plus beta. So, this is a standard equation for the emitter current, which students need to remember this. And you can apply Kirchhoff current law, Kirchhoff voltage law to the collector emitter loop for this circuit. And this circuit is very simple now to apply Kirchhoff voltage law for the collector emitter loop. Minus VCC plus IC times RC, okay, across this, plus VCE, and we have IE times RE plus IE times RE, which is equal to 0. Okay, the same equation which you can see here. Okay, from this we can derive the VCE expression here. So, VCE equals VCC minus ICRC minus IE times RE. Okay. So, now we got to know the operating point. What is the operating point of this circuit? So, operating point is nothing but VCE, we got expression for that by simplifying this, and also another value of operating point is IC, VC comma IC. But instead of IC, we derived equation for IE. Since IE is equal to alpha times IC, so that IE and IC, they are closely equal to each other. Okay. So, that is what we can see from here. So, IC is equal to alpha times IE. So, alpha varies very little, therefore, IE and IC both are equal here. So, now let us analyze this circuit in the coming class. What are the merits and demerits of this circuit? So far in today's class, we just analyzed the fundamental circuit, and later we applied Thevenin theorem and simplified this circuit, and later we applied KVL to the base emitter and collector emitter loop, and we arrived at the equation for base current, base emitter base current and emitter current, then finally collector emitter voltage. Okay. So, in the next class we will discuss the advantages and disadvantages of this classical discrete bias circuit scheme. Any questions so far?